So moving forward with completing on our mathematical formulation, let's write down all of these in mathematical expression. So suppose I denote the layers by the first layer have the size of the layers with a variable L, and let's say the first hidden layer is of size L1, the second hidden layer is of size L2, and the output layer is always of, not always of size 1, but it is equal to the size of the output. Here we are assuming the size output to be of single dimension, so output layer is of size 1. So input is of size P, hidden layers L1, L2, and output of size 1. With this configuration, this weight matrix will have a size, the weight matrix for first layer, by the way, all these superscripts 1 within parentheses means for layer 1, and this is a feature map, again parentheses corresponds to the hidden layer. Same thing here, and for output layer we have the superscript as O. So for the first hidden layer, the hidden layer is actually made up of my weight matrix. The size of the weight matrix, we can see it here. The number of rows that we have is equal to the size of my layer L1, and the number of columns I have is equal to the size of the inputted features, in this case P. The number of bias, each of these nodes will have one bias term. We have L1 nodes, so we will have a vector of biases of size L1. So this is what my first layer is made up of. The output of my first layer is a feature map of size L1. I don't know why I've written P here, it won't be here. So we have a feature map of size L1, so again a vector is Z of size L1 as an output. This output goes as an input to the second layer. And what are the parameters in the second layer? The parameters in the second layer are again a weight matrix, number of rows equal to size of the layer L2, and number of columns equal to the size of the input features. Here the input features is the feature map of the prior layer. What is the size of that? It is L1. So the weight matrix here will be of size L2 times L1, and its output, it has a bias as well. Bias will be of size L2, size of the layer, and it is sending out feature of its own size, meaning a vector of size L2. And finally, this goes to my last layer, the output layer. Since output layer has only one node, it will have a vector of weights, and the size of this vector of weights will be equal to the size of my input features as usual. So this is simply going to a vector of weights of size L2, the size of its input, and it has only one bias because it has just one. Now we can quickly see the mathematical operation that happens at these stages as well, which is simply putting what I have put here repetitively. So first layer is taking X as an input. X is here for all the samples in the batch. What is the size of a batch then? It is X, and I have NB samples and P features. With me? Actually, because we are looking it in a transposed manner, I can either write a transpose here or I can do it here. It's interchangeable, so I'll just do it here. So at the first layer, what happens is W, which is of size L1 times P, times my input plus and my activation G. If you notice here, this will give me an output of size, a feature map of size L1, and because I have NB samples as an input, this will also be times NB. Basically one feature map for each of the input sample in the batch. And then this goes to the next part where we again do the same thing. WL2 times L1 times here, instead of X now we have Z. Let me make it a matrix because it's for the entire batch. So Z is capital M, Z L1 times NB plus BL2 will give me the feature map for all the batches out of the second layer, L2 times NB. So if you see here, let me use a different color. This is the output of the first layer. Output of the first layer is a feature map of size L1 for all the samples that are inputted in the batch, and output of the second layer is of size L2. So basically each layer is emitting a feature map of its own size, and as we discussed earlier, during this process what is happening is all the nodes in this layer is solving some arbitrary subproblem and emitting the output or the finding of that subproblem inside this feature map. Then the second layer is solving some other set of arbitrary subproblems by taking the findings from the first layer as an input and giving its own output, and all of that leading to the last layer. The job of the last layer is to summarize the findings so far into one number, which is the output. So that at the last layer, this goes as an input. Let me continue it here. So in the last layer, we will have plus the bias, and we also apply another activation here, and generally the activation at the output layer is different from the activations we use in the intermediate layers. We'll understand that more when we are building the models, but still there will be an activation here as well. Let's call it sigma. So sigma of this mathematical computation will ultimately yield me the output. The output is, let me write it down like this is 1 times L2, easy understanding. Therefore my output is 1 times NB, which is basically the output for each of my input samples. So let's summarize the mathematical operations once more. Each of these hidden layers are actually made up of a weight matrix and bias. The size of the weight matrix is equal to the size of the hidden layer times the size of its input. Bias is simply a vector of the size of the hidden layer. The mathematical operation is an affine transformation, which means weight times the input plus bias, and then an activation, which is a non-linear function, is applied on top of this affine transformation to get a feature map, and these feature map acts as input to the subsequent layer, ultimately leading to the output layer to yield the output, the predictions or inferences. For each of the input sample, we have the corresponding output. So this was a mathematical denotion of all the operations that happen here. Now with this expressions, now we'll go back to why a nonlinear activation is essential.